Welcome to part 4 of week 6. Last week, I talked about a noise model that represents stochastic spike arrival. This week, so far, I talked about an escape noise model. So what's the relation between those two noise models? In the first lectures of this week, we mainly looked at the escape rate, which describes the instantaneous rate that the neuron may fire despite the fact that the deterministic trajectory has not yet reached the threshold. Now, in the previous week, we looked at a model describing stochastic spike arrival. If you start with the leaky integrate and fire model, there's an input current which has a deterministic part which gives rise to the red trajectory here. But then because of the additional noise that represents stochastic spike arrivals, there would be a real trajectory which is slightly different, which fluctuates around the reference trajectory. And in each trial, the actual trajectory is slightly different. So this actual trajectory stays in some neighborhood of the reference trajectory. If you want to link the two noise models, we need to look again a little bit at this model of stochastic spike arrival. As we have seen last week, a spike train, described as a sequence of delta pulses, is filtered, and this gives rise to a signal. The signal in the end will be the membrane potential, but let's keep the mathematical treatment general right now. The stochasticity is in the spike train. If you look at the mean, then the mean is just over the stochastic spike train. Now, in the case that the stochastic spike train is generated by a Poisson process, then this just gives the instantaneous rate of the Poisson process. We can also look at the correlations. So this is the correlation of this signal x at time t with its value at time t prime. And again, the expectation signs can be moved inside, and so we see that the autocorrelation of the input is linked to the autocorrelation of the output. Now here, x was some arbitrary signal. Let's consider now the case of a membrane potential, u, generated by a differential equation, where the drive are spike arrivals. Suppose that there are some synapses that are excitatory, and there are other synapses that are inhibitory. An excitatory spike arrival causes a charge delivered to the membrane called QE. This instantaneous delivery at that spike arrival time of the charge QE gives rise to a positive jump of the membrane potential. Inhibitory synapses would deliver a negative charge QI. Now, suppose that these spikes arrive at some frequency, excitatory rate nu e, inhibitory rate nu I. Now this mean drive causes a mean input current, a time-dependent deterministic input current characterized by the rates nu e and nu I, the two different synapse types. Now let's suppose that we increase the frequency, we double the frequency in each of the input channels while decreasing the jump size, decreasing the charge delivered per pulse. Now if we increase by a factor of 10 and decrease the jump size by a factor of 10, then there are many jumps. The frequency is very high, but each jump makes only a very small contribution. And it's this limit that gives you a white noise input of some characteristic amplitude. Let's call it sigma. And a differential equation with a deterministic part plus this white noise input is called the Langevin equation. The specific linear differential equation with this noisy input is called the Ornstein-Uhlenbeck process. Now normally, in this Ornstein-Uhlenbeck process, we don't have a threshold. A real integrated fire model, however, does have a threshold. Suppose now that we simulate an integrated fire model. After a spike, we start at a reset potential UR, and we integrate up to the threshold theta. And we do this several times. Each time we start at the reset value UR, here equal to 0, and then we have many sample trajectories. Now this is the mean trajectory evaluated at different moments in time. And you see that if you look at this moment here, let's call it T1, then the mean is different than at the later moment, say T2 over here. So this trajectory, this value here, would be U0, the mean at time T2. Now let's look at this time. Let's just do a vertical cut across all these different samples of membrane potentials. I put here the vertical axis, which is the axis of membrane potentials, and then I build a histogram of how many values do I see here. For example, I see a value here, I see a value here. And if I build this up, I will get some distribution of membrane potentials. Now, if I have many different trajectories, many trials, all starting at the same reset potential, all driven by the same deterministic input I of t, then I can build up this distribution of membrane potentials, which is P of U, now evaluated at this specific point U of T2. It has a mean, and this mean is this value here, U0, the mean at time T2. And it also has some variance. And the variance is what we can calculate mathematically. Now, in order to do this mathematical calculation, we assume for the moment that there is no threshold. So this could be achieved simply by removing the threshold or by putting the threshold to such a high value that in practice it's never reached. And then we assume, as before, that the trajectory starts at some known value, for example, the reset potential. Now, if we do this math argument, then what we'll see is that there is this variance of the different trajectories, which I can plot here, or I can point it out here. There's the variance here, there's a variance here, there's a variance here. And this variance is small at the beginning. In fact, it's 0 at time 0, because all trajectories start at the same value. And then it blows up slightly. Now, one can calculate this, and one finds that there's a final value of the voltage distribution, the variance, the standard deviation of the voltage distribution is sigma u. The variance is sigma u squared. And this final value is reached over time. And the standard deviation at the beginning is much smaller than at the end. The standard deviation does not increase infinitely. It saturates at some final value. And this is expressed here. That's the final value, and that's the approach towards this final value. Now, the mean, this value u0, the mean at any moment t, can be calculated by considering the equation just up to this part here. We integrate the deterministic part of the input current. Let's show this in 3 examples. In each case, we will consider the distribution of membrane potentials, and this distribution of membrane potentials is a Gaussian with a mean value u0 and a certain variance. U of t is one sample trajectory. So this is the probability density that at time t I would find a trajectory at the value u. The distribution is Gaussian with a center at u0 of t. So here are the three examples. Suppose for the moment that the input is stationary. This could be a constant deterministic input, or you can think of constant input rates with Poisson spike arrival. And as before, there's no threshold. Then I have a distribution of membrane potentials. And in each trial, it's a slightly different trajectory. But if I project the trajectory out onto the vertical voltage axis, I find a distribution, and this mean value, u0, is constant because the input is stationary. So, for constant input, this mean value, u0, would just be r times I0, and the width of this Gaussian distribution is controlled by the amplitude of the noise signal here. Second example. As before, there is no threshold, but now we have an input to the neuron, which is oscillatory. And I add to this input a noise term with zero mean. Now, integrating this oscillatory input will give rise to an oscillation of the membrane potential with the same frequency. Actual trajectories stay in the neighborhood of this reference trajectory. If I evaluate the distribution of membrane potentials at some point here, I will get some distribution. Let's call this T1. Then this is centered around the mean trajectory, around the deterministic trajectory, u of T1. And the distribution has a certain width. If I evaluate the distribution at some other point in time, I find again a Gaussian distribution of the same width, but with a different mean. In other words, the distribution as a whole will periodically move up and down, up and down. Third example. Now we add the threshold. We have stationary input. So the input itself is stationary. However, each time there is a spike, the membrane potential is reset to the reset value UR. And after the spike, integration starts again. So the mean trajectory, the reference trajectory itself, is time dependent. It will saturate at some fixed value. The actual trajectories are different. And they may reach the threshold at some moment in time before the reset occurs, and then the whole process starts again. If you go on with a simulation of such a stationary process for a long time, and again we project out all the different voltage values, we find again a membrane potential density. In this case, it's not Gaussian. It cannot be Gaussian. At the threshold, the density for white noise input is always zero. So if you go back for a moment to the superthreshold and subthreshold discussion that we did last week, then we see in the superthreshold regime, a lot of density is just below the threshold. The density at threshold is zero. The distribution is highly non-Gaussian. Whereas in the subthreshold regime, the distribution is nearly Gaussian. It's not perfectly Gaussian, because a Gaussian always has a finite width at the threshold. But if you are far enough below a threshold, then the distribution is well approximated by a Gaussian. So, With my model of stochastic spike arrival, I can calculate distributions of membrane potential. Moreover, I can calculate something like the mean interval. One trajectory for stationary input may hit the threshold here. Another trajectory much later. A third trajectory over here. The last spike has occurred here. That was the moment when the reset happened. Now let's look at the interspike intervals. There are short ones and there are long ones. The distribution of interspike intervals has some mean, and we can calculate the mean interspike interval. And this is a famous formula. What you see here is the mean value of the noise-free trajectory, h0. What matters is the distance of h0 to the threshold, normalized by the width sigma of the membrane potential distribution. Another important quantity is the difference between the reset potential and h0. Now, knowing the mean interspike interval for stationary input implies that we can calculate the mean firing rate of a leaky integrated fire model for stationary input. And the mean firing rate is just 1 over the mean interval. Now, let's look at the escape process for a moment. For the escape process, we have the escape rate, and we can calculate the interval distribution given the last spike occurred at t hat. What's the probability density the next spike occurs at t, knowing the input? And the formula is the one we discussed this week. Now, importantly, this can be evaluated for constant input or for time-dependent input. For constant input, we can evaluate the interval distribution. Therefore, we can calculate the mean interspike interval. Therefore, we know the mean firing rate for stationary input. But moreover, in this case, we can also calculate the time-dependent interval distribution. And that's something that's rather hard to do in the other case. In fact, calculating this quantity, time-dependent interval distribution, for the case of a diffusive noise model is classified as the first passage time problem. And if a mathematical problem gets a name, that means it's difficult. Let me summarize the first part of lecture 6.4. For diffusive noise, we are able to calculate the distribution of membrane potential. We are able to calculate the mean interspike interval for constant input. But the time-dependent case is difficult. The advantage of an escape noise formulation is that we have access to the time-dependent interval distribution. Now the question arises whether the diffusive noise model can be approximated by an escape noise model. And that's the topic for the continuation of this lecture 6.4.